Good afternoon, everyone. Today I'm going to talk to you very interesting polymer composites, which is strongly respond to humidity and light, which is giving very interesting motions. So this kind of material can be used for design of some device for generation of the electricity to realize the energy conversion from humidity to mechanical work. I would like to show you these two pictures at the start of my today's talk. So nowadays in any countries, the environment has been contaminated seriously. So clean up these plants. The environment was contaminated seriously due to the coal-fired power plants. So clean up these plants and finding cleaner alternative energy source is the overall objective to achieving clean, healthy air in every country. So today in my presentations, I will be mainly talking about the energy conversions. So from nature, we can find lots of the phenomena about the energy conversions, such as the conversion of the sunlight or water into other energy forms by just the plants. And for example, this is the iridium seed, so which upon connecting with water will drill itself into ground by means of the curling and uncurling cycles in order for the seed to sprout. So since plants are able to convert the potential energy of the humidity to mechanical work, so can we prepare materials in the lab to directly convert the potential energy of the humidity into mechanical work for generation of the electricity without any contamination to environment? So our thought actually very simple. We can combine the humidity-sensitive actuator with electric transfer as a generator. So for the humidity actuator can convert the potential energy of the humidity into mechanical work, so which can be further delivered to the generator for generation of the electricity. So with this idea in mind, the hydrogel materials were used for this, utilized for this purpose, because the hydrogel materials are water soluble and have very good solubility. After water surveillance. So we think if these materials was prepared into a thin film, so this film should be able to, by water surveillance, so inducing the mechanical instability, so to realize the energy conversion from the humidity to mechanical work. And in my work to get a better mechanical stress for the film and photochemical response, one light-sensitive polymers was also prepared and embedded into the hydrogel matrix. And here you see we use the agarose as a hydrogel matrix. So after a simple hybridization process, then the films with various thickness and can be containing around 10% of these polymers can be prepared. You see the prepared films have a silicone-like appearance and can be mechanically sustainable without the support. So these films actually have very high ability in water surveillance, water absorptions from just the environment. So when the films were kept on a support, exposure to humidity from one side, you see the films able to deform very fast, just caused by the expansion due to the absorption of the water from the right side. And the humidity-induced bending of these materials is in direction. So it means the films always bend away from the humidity source. So we noted that the bending of the films just requires the humidity as the only energy source. This can be demonstrated with these videos, you see. So when the films was placed on a moist substrate, the motion starts. immediately. So, but when the films was removed from the moist area to the dry area, you see the motion stopped immediately. So, but it can be reacquired by putting it back to the moist areas. And if you expose the films to the humidity alternatively, you see the motion can be doing repeatedly. So this process can proceed many times without apparent fatigue. So, and you know, the isobanding units was introduced into the film, hybrid film, to elicit the response to UV light. So when exposure to UV light, the isomization of the isobanding units induces the bending of the films. So the bending is more pronounced at a higher density of the UV light. And when the power density is identical, and the thinner films were more elastic, they are deformed faster with the higher degrees. So when other parameters fixed, the longer ribbons seems to be more soft. So also shows the more pronounced bending. So in response to UV light relative to the short ribbons. When you place the films on moist substrate, it's able to turn over frequently. So the turnover frequency can be influenced by the thickness of the films. You see, when the thickness is around 20 micrometers, it's very thin. So it's able to move on most substrate very fast. So the frequency getting up to around 150 per minute. So really fast. But if you increase the thickness of the films to around 200 micrometers, greatly enhance the stiffness of the films, but also decrease the frequency to only around 5 per minute. And the temperature also affects the frequency of the films on the motion on the moist substrate. So the best temperature for the motion of the films on moist substrate is around 35 degrees centigrade. You know, that is very close to physiological temperature. So when these films was kept on a support, you see the film deflected when approached with a finger and retracted when the finger is removed. So if you place the films on pump, you see the films can move across the pump just by absorption of the moisture from your skin. So actually, this video is further demonstrated the best temperature that is around 35 degrees centigrade for rolling over of the films on moist substrate. So to demonstrate the capability in mechanical work, the films loaded with cargo and placed on moist substrate. You see, the film with cargo even can move at the weight ratio of the cargo to the film of getting up to 20:1. You see. So here, driven by humidity, this film can act even as a cantilever current, of course not a real cantilever current. So you see, the films can harvest the energy from humidity and convert it into mechanical work. Here you can note the ratio of the films and the cargoes. This means the films can generate very strong bending force just by absorption of the water, which causes the swirling of the films. So, and as a general proof of the concept of utilizing the humidity in biomimetics, we designed the soft robots, so which are capable of motion and can carry cargoes in response to extended humidity. So if you design the films into a paper dough shelves, you see application of the humidity, you can induce the opening or the closing motion of the paper dough. And a similar motion can also be found with these, the films-based very simple switchers, you see. Yeah. And the kinematics and the mechanisms of the locomotion depend on the ratio, aspect ratio of the films. You see, we found the square and the rectangular films have very similar motions just on the most substrate, but the locomotion of the strips proceeds in different ways. You see, when the strip of the films was placed on a moist substrate, the asymmetrically swirling caused the strips to distort from both ends and then twist and suddenly top over. So again, by absorption of the water, so caused the distort, then going to the next cycles. So as you see here, the motion, the film in motion, the motion of the films can be modulated by the UV light on most substrate. You see, when the films in motion was exposed to UV light, the motion stopped immediately. So the films resumed its motions as soon as the excitation was determined. So to further demonstrate the photogating effect, a bending film was exposed to UV light. And here is humid air was applied to the films to induce a slowly bending. Then exposure to the UV light resulted in the films bending away from the light source and against the airflow. So these videos, indicates the possibility to remotely control the motion of the humidity induced motion just with UV light. And we can understand the mechanism of the photogating effect on the motion of the films. So, these films was prepared from two kinds of polymers. So one is sensitive to UV light. The second is sensitive to humidity. So if you just apply one stimulus to the films, of course you can just get only one response, the motion or the bendings. But if you apply both stimuli together to the films, definitely there will be interactions between two stimuli induce the force, right, to the films. So when the humidity induced the down to top bending force is same as the light induced the top to down bending force to this film, the motion will stop. So resulting in the photogating effect. By using the same aggregates as the matrix and with another fluorescent molecules, we also able to prepare another composites, smart composites with exhibiting very interesting color changes in response to the pH. You see, the dry films is colorless, but able to display very strong fluorescence under the very weak excitation of the UV light. And so when soaked in the alkaline solution, you see the emission color, the hydroxy group of the fluorescent molecules can be deprotonated. So the emission color of the film immediately changed from the blue to yellow. And the blue color can be recovered just by immersion of the films to acidic solution again. So, and these films with the color change between blue and yellow can be used as a template. Means you can just use the alkaline aqueous solution as the ink. You don't have to use the real ink. Then you see you can write some information on these films, and of course these films can be used repeatedly because the information can be removed just by using the acidic solutions. And see, the information is readable under the visible light or the UV light. And we know the sunflowers, right, which moves always towards the sunlight, so showing a very high sensitivity to light. And you see, so agarose and fluorescent-based films is so multifunctional, so which is not only to respond to pH, but also sensitive to the light, which gives some motions. You see, one excitation with the UV light, the isomerization of the fluorescent molecules induce the deformation of the films. So depending on the aspect ratio, the deformation persists as the spiraling and twisting. A control test confirms that the deformation of the films is due to the light-induced isomerization of the fluorescent molecules, not because of the photogating effect. Because usually if you shine some materials, the light you normally can generate the temperature increasing. So, but here you see the light irradiation just generates around 6 degrees centigrade, the increase of the temperature, so very low. That temperature is not able to induce the bending of the films. So, so here we use the UV visible spectroscopy to confirm the trans to cis isomerization process. So when excitations of the trans structures changed to the cis structures, and the reversibility test indicates that the cis to trans isomerization process was very slow, because there are not enough energy applied to the films, because we just put the films into a darker condition, so to induce the cis to trans isomerizations. So in this case, that the energy is very low. But anyway, these hybrid films bending with under the UV excitations is thickness-dependent reactions. You see, the increase of the thickness greatly decreases the flexibility and the reactivity of the films to the light. But however, if you just keep the thickness at constant values, so exposure to the light alternatively, you see, it shows very nice repetitions, the bending repetitions. And because these films were made of agarose, which is actually hard gel materials, so these strips is expected to be sensitive to humidity, which gives some motions, you see. And when exposure to the humidity, it is able to curl. It shows a curling, so which is very similar to the motion of the cucumber tendrils, so which try to bend and curls to find some support to lift itself upwards, you see here. And another interesting motion is in simulation of the iridium seed. So here we combined we fixed the strip of the films on a wood coil, and then exposure to the humidity alternatively. You see, the application of the humidity induces the strip with curling and uncurling, so which drive the wood coil to spin, so continuously spin into the ground. So across here, we just use the silica beads to simulate the condition of the ground. And if you place this kind of films on most substrates, the similar motion to previous films can be also found. See. In order to expect the effect of the UV light, the films was in motion was exposed to the UV light. And for these films, we were not able to detect visible effect of the light on the motion of the films on most substrate, because here we just use a very, very weak UV light. I think if we apply a very strong UV light, it should be able to affect the motion of the film. And the final purpose of the studying smart materials is to find good applications. So these materials can be used for design of some device. And here we just design a very simple device and use electric transducers. And this transducer is based on the ceramics. Across here, you see just generate very low voltages. It's not a material same as Professor Adrius talked. So that's very strong. But this one very weak. Anyway, we just want to demonstrate here these films, the humidity sensitive films can be used to realize the energy conversion from the humidity to mechanical work. So this mechanical work can be further applied for another applications. And the conclusions in these presentations actually including two parts. One is based on the agarose and another sensitive, light-sensitive polymers. So prepared composite films can strongly respond to humidity and light with giving very interesting motions. And also the motion can be modulated or controlled by UV light remotely. And the second part, we also use the agarose as a matrix with another fluorinated molecules and to prepare another smart films. So these films not only show the light and humidity sensitivity, but also be able to respond to pH with given color changes. And finally, I would like to give many thanks to New York University in Abu Dhabi, and also Professor Panchinam for supporting these works. So thank you for all your attentions. Mm-hmm. Thank you.
Thank you very much, Doctor. Do we have any questions?
Any questions?
Fascinating work, at least to me. And a couple questions. First, how do you make these films? Is it only agarose films? How do you make it?
It's based on two kinds of, for the first part, we use the two polymers, right? So yes, we can make two polymers in solutions. We just dissolve the agarose in DMF to make solutions. Then we also dissolve the second polymers into the DMF. Then we mix the solutions. Based on solution, you can make any films. Yeah.
So the film itself basically homogeneous. It's not really asymmetric. It's symmetric, right? Okay. Yeah. Second question related to if you make let me say a string or fiber, do you see this kind of motion as well, or you have to be a film?
I didn't try with the fibers, but definitely if you make that into strips, it's possible to move, to draw over a most substrate. Yeah, okay. I already demonstrated this one.
Okay, yeah. Thanks.
Yeah, thank you.
So when you make the films, are they, have they phase separated, the two different polymers?
Yes.
Mm-hmm. And so these are not really block copolymers, they're just
linear.
Mixed.
We just mixed two kinds of polymer in solutions. So actually they are combined, I think physically, just based on the hydrogen interactions. And also for this work, we well demonstrated the interaction between two kinds of polymers by using various techniques.
So if you looked at under SEM or under light microscopy, would you be able to see the phase separation of the two polymers?
Phase separation, actually we didn't try with this kind of observation.
And the other polymer is a PEG polymer? Is that, what was the other polymer, not the hygroscopic polymer? What was the other polymer you mixed?
Which polymer, sorry?
You did agarose and DMF, and what was the other polymer you used?
Yes.
What was it?
Sorry?
What was the other polymer you used besides agarose?
It's PEG and isobenzene based polymers, and we synthesized that one. Yeah, it's like a new polymer.
Yeah, you.
Did you consider to make retaxanes of your photo switches? So, for example, if you have a cyclodextrin encircling your trans isomer, when you do photoisomerization, the cyclodextrin would have to move because it cannot fit around the cis. So you could combine your geometrical movement also with the movement of another unit along this small wire.
You mean the F-band units may be affected by the.
So if you have sort of retaxane like this, now if you do footage, you see now this cycle unit has to move. You combine that movement along with your theoretical chains. Because these retaxanes can be made in water solution from using cyclodextrins. So due to the hydrophobic cavity of cyclodextrin, these molecules would be threaded into the macrocycles.
Yes, of course. If you use the cyclodextrin, definitely that's possible because the cyclodextrin has its very special properties because it needs the channel on the after surface. That's the property different, right? But for my polymers, the agarose, I don't think it has the same properties as the cyclodextrins. So because for the 6 ring, 6 carbon ring, I think it's completely different properties. So I didn't find any similar property as you described.
Thank you.
I have a couple of questions. You said that when these films move, did you really found that how much moisture is absorbed on that, and what is the minimum thing which is required to make them active?
The humidity.
Yeah.
We studied this based on the moist substrate.
Moist surface, yeah.
Containing how much water. So we found if you use the moist substrate with very less water content, of course the film is still possible to move, but very slow because the balance between the water absorption and desorption can be constructed for long times. So anyway, we found the best condition for the moist substrates that should contain around 40% water. That's best condition. Yeah. And if too much water, the films will stick to the surface, so cannot move.
And what is really the mechanism? I mean, you have shown this structure. Water is getting absorbed, and then what is that? Is there any bond flexibility is there, or what is that which makes it move in this direction? That is, I think, the real.
The physical mechanism is because after water absorption, the films get swirling, right? So for example, this is the films. So once you put that on moist substrate, definitely this side should get
okay.
because the swirling, right? More swirling. So the film should bend up.
Okay.
Yeah. So once bend up, the weight center will change. I mean, it's the mechanical.
That's right. But somehow I think there is some kind of a physical reaction or something like that where the bond is getting elongated or something like that. That I think is the real interpretation of.
The agarose contain lots of the hydroxyls. So we can form the hydrogen bonding between the agarose and water, right?
Okay.
Just by means of the hydroxyls. So this is the chemical mechanism.
And the last question, you have given a very nice conclusion about that they can act as an actuator to hold the thing. Now with the thin film, you find that 20 times or something weight it takes. But then the problem is that if you have to take higher weights, then you have to make thick films. And when you make thick films, then the mechanism will not work.
Yeah, mechanical stress
And that's why he told the other idea, when you convert it into fibers or any other shape, then also it may not work because your mechanism of absorbing moisture on one side, and then that will not work. So in a real sense, when you really want to use it as an actuator to lift the weight, that looks to be a bit of a paradox, that whether it will really work in that way.
For my polymer films, if you increase the thickness, of course you can increase the mechanical stress, but the water sorption water sorption process will take long time. So in this case, the bending of the anyway the deformation will take a long time to happen. So means the films will be not so active.
But is there anything like you told heat, when you treat it with a UV light, then also the effect is very much, and temperature also has some effect. So I think all the three things are playing with the bonds stretching and contracting. Your molecule is very big. So when either moisture or UV light or even slight temperature, so somehow it is trying to play with the bonding of the long structure, whether the chain is getting,
It is a molecule, right?
Yeah.
I think this is possible, but the force should be very, very low due to the humidity
Yes.
induce the spreading, which is generated in the high force. So if you compare them, the force generated in the molecule